You tell me.
Good. The floor is yours.
All right. So thank you very much for the invitation. And before starting, I'd like to extend a special thanks to Gianluigi for this effort in organizing this series of talk. My name is Gabriel Raya. I'm a PhD student at JATS, which is an initiative between Tilburg University and Eindhoven University of Technology, and also a visiting researcher here at the Donders Institute of the Radboud University. A little bit about myself. I do research about the foundations of generative models, in particular in diffusion models, and I'm very interested in the connection that exists between generative models and how particle generation emerges in nature from the formation of a single particle to the emergence of intelligence. So today, I'm very happy to share our latest work accepted at NeurIPS called Spontaneous Symmetry Breaking in Generative Diffusion Models. This is joint work with my supervisor, Luca Ambrigioni. So first, what I want to show you is a little bit of the progress in generative models. Already like 10 years ago, Kigma and Welling, they started to show amazing results in EVNIS. Right now, it seems like it's an easy task, but by then it was very complex. They introduced a different approach for using the variational autoencoder, and then the community started showing tremendous progress with introduction of generative adversarial networks, or GANs, in 2014. And then another approach, which is a probabilistic approach, is Pixel CNN++, which is an autoregressive model in such a way that they constrain the architecture such that the output gives you a proper probability distribution. So compared to GANs, VAs and autoregressive models are are probabilistic models, and the main goal here is to try to have a powerful model that estimates the distribution of the data. And then the progress continues with style GANs. You see also with GLOW, which is an extension of normalizing flows. And this start to show tremendous results also with deep hierarchical VAs. But recently we have seen an explosion of these images all around the media, especially diffusion models have, I think they are the dominant approach now for modeling very complex distributions. We have also seen systems like DALI 2 and DALI 3, in which you can give a text input, which is some sort of conditional generation task, and then you will get an impressive image like this one. And these are systems that, so this basically shows the transition from doing research into real applications, which before, now it seems like it's super easy to have this performance, but before, I think people thought that this kind of performance was almost impossible, because you can see that the quality of the generated samples are impressive. And this has also been extended to video data in models like Imagine from Google, and a diverse range of applications such as this one in order to generate point clouds. This similar idea to the clip embedding in DALI 2 and DALI 3 has been used for a similar task for 3D generation. Now we have seen also that diffusion models have expand their applications to scientific fields, such as this one, to generate protein structures. So given their diverse range of and potential use of new applications, understanding how diffusion models work, I think, is very essential to ensure their responsible use in various domains. And just as a recap for people that are, or maybe that you don't know diffusion models, but the essential idea is to systematically destroy the structure in the data. So you start with a data distribution, as you can see here. You can use a process that basically maps the complex distribution to an easy to sample distribution, such as Gaussian distribution, using a stochastic differential equation. one thing that you need to know is that in this case, the drift term and the coefficient terms are fixed, such that we guarantee that the convergence of the distribution is a stationary Gaussian distribution. And then the idea is that we can have a reversible process such that once you map the data to a noise distribution, you can start from the noise distribution and reverse back to what you want to do is exactly kind of reverse the trajectories in the forward direction, so such that you move from the noise distribution to the data distribution. This is something that is called quasi-statistic process. In thermodynamics, a quasi-statistic process is something that happens very slow, such that you, at every single step, it resembles like it's a stable equilibrium state. And the main difficulty here is to learn the gradient of the log probability, because first of all, what we want to do is to model the probability of the distribution, P of x0, and we don't have any knowledge of the probability distribution. What we only have is the data. And this is done by using advanced methods for score matching, using denoising score matching by Pascal Vincent over multiple times. So in practice, as I explained, people normally use an OU process, which is also known as a variance preserving SDE. This is one of the most commonly processes that you can use. You can use different types of processes. The main constraint is that you need to basically have a forward process that maps the data distribution to a noise distribution. And then by replacing the drift term and the coefficient terms, then you get the following expression, and this is the generative SDE. And as you can see, the transition kernel basically guarantees that you will get a Gaussian distribution using these parameters that starts from 1 and ends to 0. So at the end of the diffusion process in the forward direction, this will become an isotropic Gaussian distribution. I just want to say, if you have any questions, feel free to ask or interrupt at any moment if something is not clear. So essentially, in the typical understanding of diffusion models is they see generation as a single denoising phase. As I explained, you start from a noise, and people call it you start removing the noise to move towards the data distribution. But what we found in our paper is that the generative dynamics of diffusion models undergoes a spontaneous symmetry breaking phenomenon, which essentially marks two distinct generative phases, not only a single denoising phase, but two phases, which I will explain in the following slides. But before, I would like to start with the concept of symmetry. Symmetries play a central role in the study of any physical systems. They tell us about conservation laws. And essentially, symmetries shape our understanding of the laws of natures. And we found symmetries all around us. For example, in the wings of a butterfly, we found reflectional symmetries. Also in the feathers of the peacock. We also find symmetries in the structure of the molecules, like reflectional symmetries, rotational symmetries. And we also even find symmetries in art, in artistic works. And in the same, we use symmetries to express the laws of physics. But perhaps one of the most important concepts of symmetries is that of when a symmetry is broken, describing the transition from a higher to a lower symmetrical state. And this is essentially what gives rise to pattern formation in nature. As an analogy, we have the example when you have a transition from liquid to crystal. You can imagine that the liquid here, you have rotational and translational symmetry. But after some critical time, in this case, after some critical temperature, the state of the water transforms into a state of lower symmetry, in which now we have a fixed orientation. And you can see this as a transition from a disordered state to an ordered state. And as stated by Gross, the secret of nature is symmetry, but much of the texture of the world is due to mechanisms of symmetry breaking. But also we have that asymmetry can be spontaneously broken, resulting in what is known as spontaneous symmetry breaking. And this is typically described by a Mexican hat potential, as you can see here, or can also be described as by a pitchfork bifurcation diagram. The Mexican hat potential represents the potential energy, showing that systems fall into a new lower energy state. And this is also reflected by looking at 1D section. What you see is that a single particle has a equal potentiality. And as it moves to a lower energy state, at some point, what you see is a split in the shape of the potential. And this is also what you can see at the same if you analyze it as a bifurcation diagram. So this is at the core of spontaneous symmetry breaking, as we will show later. But it is so the concept of spontaneous symmetry breaking is very relevant in nature, which describes the thermodynamics of phase transitions. It also describes the emergence of various phenomena such as crystals, as shown in the previous slide, and also the emergence of magnetism and broken gauge symmetries. What is very interesting is that the concept of symmetry breaking has not yet been examined in the context of generative models, contrary to the effort that people have done in deep learning to encode symmetries. The concept of spontaneous symmetry breaking has been so far until now unexplored. So what we found in our paper is that the generative dynamics of diffusion models undergoes a similar phenomenon, demarcating a phase transition from a higher to lower symmetric state. As you see in the image, what we found is that if you analyze the diffusion model in a one-dimensional case, you see that the potential splits after a critical time. And you can also analyze this for higher complex data distributions. What you found is a similar behavior. And as a result of this, we found that the diversity of these models comes essentially from this window of instability, and this touches the connection between critical phenomena in statistical physics. So to show the existence of spontaneous symmetry breaking, we first need to express the generative dynamics in terms of a potential energy function. So far, I would like to stop just to make sure if there's no questions or everyone would like to ask something so far. No questions? Okay. So what we can do is to express the potential in. So what we need to do here is to express the generative dynamics in terms of the potential energy function as follows. And then the way we have the understanding of the generative dynamics is as the following expression. In this particular case, for any diffusion process, the potential of the generative dynamics of the diffusion process is expressed as follows. In our analysis, we focus on the very use variance preserving SDE. For this particular case, the potential energy function has the following expression. So in order to analyze how the split of the potential energy happens, we first need to define an associated symmetry group. Basically, once we define an associated symmetry group, we can define also a pair of fixed points using this. And what we want to analyze is the stability of these the stability of the path of the fixed points. So we can analyze the stability of the path using second partial derivatives, and this is what we're going to do in our theoretical analysis. So we can theoretically show the existence of a spontaneous symmetry breaking in a one-dimensional diffusion model. For this, we propose to assume that the data comes from a mixture of two delta distributions. In this case, the potential energy, the symmetry group that preserves the potential is the identity and the reflectional symmetry. In this case, we can estimate the marginal as follows. So in this case, this is the marginal of the forward process. Essentially, what is important here is to know that we can estimate the marginal. This is typically not the case for high complex distributions in diffusion models. But with this, we can now define the potential energy using Anderson theorem, which basically tells you that due to the reversible process, you can assume that the marginal matches at each time step the forward process. The marginal of the forward process is equivalent to the marginal of the reverse process. Using this insight, we can find the analytical expression of the potential of the generative dynamics of a one-dimensional diffusion model. This is just to summarize the fact that we can prove exactly the analytical expression of the potential for a one-dimensional diffusion model. And with this expression, we can now simulate the generation of a particle. This is how you will think about the generative dynamics of a single particle. Next, we did the evolution of the potential. So for all values of t, the gradient vanishes at x equals to 0. The potential is symmetric on the reflection, but as you see here in the, I will run again the evolution. So this gives us a different insight of how a particle generation is understood, because we can analyze this and say that this, so intuitively we can think as a single particle to be generated with equal potentiality, and after this point becomes only the denoising phase. So all fixed points can be found by solving the self-consistency equation that we can obtain analytically. And by solving this equation, we can find all the fixed points, as you can see in this graph. And this will give us the pitchfork bifurcation, which shows the existence of a stable fixed point at the origin. The way you can think about this stable fixed point is that once you start sampling, there is a single stable fixed point that is basically the origin that comes from the Gaussian distribution. And after some time, the stable fixed point becomes unstable and then branches into two new stable fixed points. So the way we interpret this is that there exists two generative phases. One phase, which is a phase with equal potentiality, which is mean reverting. And the second phase, which is an attractor, which reflects an attractor dynamics, and what we call this the denoising phase. So this is basically what is this provides a different insight into what people call that the generative dynamics has a unique single denoising phase. This tells us that there is an early phase, which is mean reverting, basically doesn't really contribute to the generation of the n particle, but that all the information of the diversity comes from this critical area. Okay, so this is a summary of the overview for one-dimensional diffusion model. And as you can see here, there's this early phase, which is mean reverting to the fixed point. And after this critical time, then we have the split. And then this behaves as an attractor, pushing the data towards the data, pushing the particle towards the data distribution. We now present empirical evidence demonstrating the occurrence of spontaneous symmetry breaking.
Can I ask a question, Gabriel?
Yeah.
So basically, what this analysis shows, if I understand correctly, is that for the first part of diffusion, there is nothing really happening. It's like there is just noise, keep being noise, and then at a certain point, the diffusion process will diverge or will sort of move towards the distribution of the data points, right? Of the data set.
Exactly. Yeah. I think you put it in better words. That's exactly what is happening, as you can see here in the simulation. So you see that the particles are. So this movement is just due to the fact that we are characterizing the potential function. Let me go back to the equation here. So we are just characterizing the dynamics as follows, right? So we are checking the change in the potential plus the noise. Essentially, what is happening is just what you said, that at the beginning, everything moves around, but due to the stochasticity that comes from the diffusion term, right? So all of these things here and then just bounce around, but it stays near or very close to the fixed point. So you can imagine that there's like a single point here, and then it moves around. But if you remove the so let's say in the deterministic case, you will basically see that the fixed point just stay there. Let me show you. And we also in the paper we also provide the analysis for the deterministic case. Go again to the simulation. But essentially what is happening is that if you remove the stochasticity, you will find that the particle just stayed here at the fixed point. Maybe this is a bit confusing at the beginning, but what you can think here is that this is the single particle that you sample from the Gaussian distribution. And there is such a fixed point that the dynamics are reverted back to this initial state. So one way that you can see this, also the way that you can see diffusion models, is that you have two stable states, which is basically the data, and you have the other stable state, which is the stationary distribution. And at the early phase of generation, you have this stable point, and everything remains at the stable point, and it just moves around due to the stochastic behavior that comes from the diffusion process, that comes from the diffusion term. And that's why we can say that, for example, the particle passes from an initial phase with equal potentiality. And at the beginning, every single particle can be randomly sampled. So it doesn't really matter if in this case, let me see if I can stop the generation. So what you can see here is that at the early phase, these particles really doesn't contribute so much for the generated particle at the end, because essentially nothing much is happening after a critical time. And that's the essence. After a critical time, something happens and it spontaneously breaks the symmetry. And then after that point, you see that, for example, in this mixture of two delta points, we define that the data comes from either -1 or 1. And after that critical time, then suddenly the dynamics decide where to go. And this is also related to something that is called in control theory as the delay choice mechanism, that you delay the decision till very end, because if you are far from the point that you want to go, there's a lot of uncertainty, and then as soon as you get closer, the uncertainty decreases, and you need to make a choice. And after this critical time, then indeed this behaves as a denoiser, because it already decides which point wants to move towards the data. And that's essentially, yeah.
Okay, and what you're plotting there on the right-hand side is the potential function up there evolving with time, right?
Yeah, so this is the potential as it moves through time, yes.
Okay.
So you see the potential is a function that depends on the noisy state and the time. So as shown before in the previous equation, we re-express the generative dynamics in terms of this potential function. But what we see in both is just equivalent to each other. So we are looking at the path of the generated particle, but we can analyze the same behavior, but just this is a different way to visualize this. But what is interesting from this point of view is that we actually propose to interpret the generative dynamics in terms of an energy function. And this connects the idea from statistical physics that you have a free energy that you want to minimize. You can also interpret this so basically that the system wants to go to the state with lowest energy, which is 0. As you see here, the system tries to minimize the energy. And then at some point, you have to, So it wants to move to the vacuum state, what is called the vacuum state, but there's two. At some point, this is something that is called the degeneracy, because there's two vacuum states. So the system can choose either between one or the other. And this is basically at the core of what is known as spontaneous symmetry breaking. Yeah, is that clear? Or any other questions?
Thanks.
Any other question? Maybe. Yeah, and you can see this probably in a better way, because here with the bifurcation diagram, you can see that the stable fixed point remains stable up to the critical time, and then it splits into those two points that you saw in the potential. And this is just the potential next to the different paths of the generative dynamics. So here I will provide the empirical evidence in trained diffusion models. So to investigate how the bifurcation affects, as I showed you, that the bifurcation remains stable after a critical time. What we propose is to analyze this, to analyze the impact of a late start initialization. So typically in a diffusion model, you start time equals 1000, and then you start denoising back towards the initial state. So what we propose to analyze here is to, rather than starting at time equals 1000, start the generation before. What we found is that the performance remain stable up to a certain point, as you see here in the FID curve. So these are the FID curves of the performance of the model for MNIST, ImageNet, CIFAR10, and Celebrity A. So basically what this means is that we analyze the performance. So you typically analyze the performance of generative models in terms of the Rechet inception score, which is the FID score. And in case of CIFAR10, the FID score would be around 3.0. And then what we would expect is that if you start before the initial time, so let's say at 1000 time is the equivalent where the isotropic distribution is the stationary state, you can start before that. And of course, you might expect that by using the same sample coming from the isotropic distribution, you will get something different. But what we found is that there is an early phase that remains unaffected, as you see here. And even in some cases, I found that in CIFAR10, for example, in some cases, you found even better FID performance if you start before that. So that seemed a little bit strange at the beginning, because you can say, yeah, I mean, how this happens, because if we are starting at a different state, then the distribution already shifts, is slightly different to the isotropic Gaussian distribution. And as you see in the quality of the generated sample, so this is what you get. So you get this is a typical way that you sample if you start t equals to 1000. And you see that the quality of the generated samples remains the same, even if you skip like 200 steps. So this is immediately a way to accelerate sampling in diffusion models just by properly sampling before that. So this indeed tells us that there is this phase or early phase that remains unstable that significantly contribute not much to the final generation. But then we also found that there is, after the critical time, there is an apparent discontinuity in the second derivative of the FID curves. And this is also what it touches with the phenomenon of spontaneous symmetry breaking, because at this point, correlations are infinite. And well, something else that you can say from here is that this basically connects what we show in analysis of the bifurcation, that there is a initial point that remains stable, and after a critical time, it bifurcates. And I will tell you a little bit more about this, about the insights, how we can use this to improve the sampling in diffusion models. But before that, so studying the stability of the fixed points in trained diffusion models is challenging, because we cannot analytically compute the marginal. So what we propose here is instead to analyze 1D sections of the potential by taking two interpolations between two generated paths. So what we did is to basically generate two samples, and then we get a single path going from the isotropic state to the data distribution, and then we do circular interpolation between them. And by that, you can actually show 1D sections of the split in the potential. We provide this for, in the case here, for CIFAR10, and this is an average over 20 generated samples. We provide the same results for ImageNet 64, and again, you see in the left, these are the generated samples by the diffusion model, and these are the split in the potential. And what you found, again, is that the potential is split after a critical time. But just one thing to notice is that after the critical time, there is a split. Then after also there can be several splits. So these tell us that there's not only, like in the 1D case, that there's only 3 fixed points. In this case, there are several fixed points that may exist several bifurcations after the critical time. And we also show here for the case of Celebrity A. So now I will tell you how we can leverage spontaneous symmetry breaking to improve the performance of fast samplers through a Gaussian-led star initialization. So typically what you do in diffusion model, as I told you, is to start from the noise distribution and iteratively move to the data distribution by using typically 1000 denoising steps. So sampling is pretty slow in diffusion models. And for that, there has been a lot of work trying to speed up sampling. One remarkable work is this of Song in 2020 called denoising diffusion implicit models. And the idea here is that you want to skip as much as possible. But of course, these fast samplers have the trade-offs, basically the big trade-off between quality of speed. So if you want to go faster, then you need to reduce the quality of the generated samples. But of course, that's something that people want to have in industry, or for example, when you are asking DALL-E 3 to generate a single sample, you want it fast, and then you don't want to wait 1000 denoising steps, so you want to have it in 5 seconds or even 1 second. So what we found is that implicitly these fast samplers, they implicitly sample at a time lower than capital RT, for example, and you see this coming from the code of the implementation of the DDIM sampler. They use an open interval. In this case, the number of time steps is what I said, 1000. So if you want to generate a single sample in 5 denoising steps, you will get the following sequence of steps. So they implicitly skip the initial state. So that's also a bit strange, you may think, because at this point they still sample from the isotropic distribution, and this is something that empirically they propose. And there are other types of approaches that people are trying to use empirically to try to get better performance. But indeed, our analysis tell us that the early dynamics are approximately linear and mean reverting. And we also show that basically there's nothing much happening in the early phase, and the Gaussian distribution remains close to a Gaussian distribution, and you can assess this by using a normality test like the one we have here. We use a Shapiro-Wilk test to assess the normality. What basically you see here is that after a critical time, for example, in the case of EMNIS, it remains very close to the Gaussian distribution, the same for CIFAR10, ImageNet, and Celebrity A. So what this tells us is that you can actually just propose a Gaussian approximation, and that's what we did. So we proposed to use a multivariate Gaussian approximation by just taking noisy samples. So what we did is to use the forward process to get a at a single time a noisy version of the data. So you get xt for different inputs, and then you feed that to a multivariate Gaussian distribution, so you get the mean and the covariance matrix for that. And then what we propose is to, rather than start the sampler using the isotropic distribution, we use our Gaussian layer star approximation and then run the sampler at that time from there. And what you see here is that you can actually, in the case of DDPM, which is the typical, this is the noisy diffusion probabilistic models. You can use the equivalent of this for the deterministic case. The paper of DDIM showed that you can use this for fast samplers. In this case, you can just obtain these samples using 5 denoising steps. But you can also, rather than initialize that using the isotropic Gaussian distribution, you can use our Gaussian layer star initialization. And you can see that you obtain better FID scores. Notably, you obtain great diversity in the generated samples that you can see. For example, by using the Gaussian layer star initialization, you get more diversity. For example, in this one, you just get people that are basically white people. In this one, you get people, Asian people, colored people, blonde people. So you kind of resemble more the diversity that is in the data. This is indeed very relevant for real-life applications. Then these are the complete results that we obtain after running the Gaussian layer star initialization for different data sets and for different samplers. The DDPM basically resembles the stochastic dynamics. We also show that you can extend this for fast samplers such as the DDIM and the pseudonumerical diffusion fast sampler for 10, 5, and 3 denoising steps. And you see that in overall, the Gaussian layer star initialization can boost the performance of all these samplers. So one thing to note here is that our goal was not actually to improve the quality of the generated samples, but as a side effect of the analysis, that we found that the diversity comes if you reliably can sample in that region of instability, you can obtain, and you can basically boost the performance of the sampler. So you can use these insights to basically boost the performance of all the samplers that people are using for LE3 or distillation approaches. So finally, we also provide a diversity analysis of fast samplers to illustrate that achieving high diversity depends on reliable sampling within the critical temporal window of instability. Notably, our Gaussian layer star initialization significantly enhance the diversity of the generated samples. As you can see here, what I showed you is that the diversity in the trained data set has the following shape. No? If you only look at the colors, you can see that the diversity is, there's a dominant presence of white people, Latin people, Black people in green, Asian people in red, Middle Eastern in blue, and Indian in brown. When you only use the typical way without accelerating the sampling of diffusion models, that means that if you sample using 1,000 steps, so no skips between the denoising steps, you get something that is very close to the data distribution, to the training set. So that's why diffusion models are pretty strong, because they also cover fully the diversity in the training set. The problem that you see in practice with biases towards that is because people want to go faster to get sampling in a short time. So you see that once you use methods like DDIM, using only, rather than using 1,000 steps, you only use 5 denoising steps, you indeed have this trade-off between quality and speed. So you basically sacrifice diversity for speed. As you can see here, basically the amount of Indian people is almost, it's almost gone. And it overemphasized the presence of white people. sorry, I was talking about this diagram. So this is what you get in the typical case when you use the fast sampler. But if you use our Gaussian approximation, you basically increase the diversity of the generated samples. So in summary, we show that the generative dynamics of diffusion models exhibit spontaneous symmetry breaking, resulting in two distinct generative phases: a phase one, which is a linear steady-state dynamics centered around a fixed point, and an attractor dynamics that guides the model towards the data distribution. And there is this period of instability that is responsible for the diversity of the generated samples, and this touches the connection between critical phenomena in statistical physics. And we propose how to leverage spontaneous symmetry breaking by using a Gaussian later start initialization. And we show how this can improve the results up to 3 times in FID improvements. In conclusion, we show that the early phase doesn't significantly contribute to the model performance due to the spontaneous symmetry breaking phenomenon. Thank you for your attention. And now, yeah, I would like to take any questions if there is any questions that you would like to ask.
Yes, I have a question. About the Gaussian late start. If I understood correctly, so what you do is that, well, it's not a question, it's a clarification actually. Yeah, if I understood correctly, you take the whole training data set and then you diffuse it forward, so adding noise, until you get something that is more or less Gaussian, right? And then you fit a multivariate normal distribution to that distribution, and then you start from there. Is that correct?
Yeah, but we don't take the whole data set, so we also you can also have an approximation for that. So what we do is, so we just take the forward process, right? So we show that you can actually use the transition kernel to get a noisy estimate. So you only take, for example, if you want to approximate it at this time point, what you can do is just to take that forward. So basically the T-step transition kernel to get a noisy estimate of this. And then what you can do is to take a single batch. For example, you can just take a single batch of 100 samples, and then you feed that to the multivariate Gaussian distribution. There's no need for using the whole data set. We show that you can actually just take a small percentage of the training distribution, and you get the same, very close to the same results by using the whole training set. Mm-hmm. But essentially, yeah. So essentially, you just get a noisy a set. So basically, a batch of noisy states here, and then you feed that to a multivariate Gaussian distribution. Yeah.
Okay, and this is done because for any data set, the how do you say, the diffusion steps, right, in between of the forward process are not going to be exactly isotropic Gaussian, right? So then you need a multivariate distribution to approximate the actual distribution at that time step.
Yeah, exactly. So that's something that is yeah. So essentially, what you have here is that you are just mapping the data distribution to the isotropic Gaussian distribution.
Mm-hmm.
Yeah, so essentially what you have here at the end is that at this point, it converges to a stationary Gaussian distribution, but we don't know exactly what is the distribution at this point, right? So yeah. if you want to start the generative process at this point, so there are some distributional mismatch. So that's why we propose to use this Gaussian approximation, because what you want to is to minimize the distributional mismatch by having a late start. What was weird, or also a bit weird, or more like probably the insights that people from Stanford, they found that they just use this point, for example, time 800 rather than time 1000, but they still use the same sample coming from a from an isotropic Gaussian distribution. But of course, at this point, the distribution is slightly different from the one that you have at the end state. So that's why we propose to use that to basically just to minimize the distributional mismatch. You can also approximate this Gaussian distribution by other approaches. For example, you can also fit a VAE, for example, and then you can use the distribution approximated by the VAE to start the denoiser.
Mm-hmm.
Yeah.
Perhaps a more naive follow-up question, but how early, how soon in the forward process does the distribution become too complex to approximate? You see what I mean? Like if you you could naively just diffuse very few steps and learn a very complex distribution of the data, but in your experiments at least, how many diffusion steps were necessary to make the distribution simple enough to fit?
Yeah, so exactly that's something that in practice maybe I can show the. So in practice, you also need to basically do an ablation study to find what are the critical points, right? Because the idea is that we can only estimate analytically the critical time in a 1D dimensional case. But the idea is that at this point, you should sample. And we also show that before the critical time, in practice, the distribution remains close to multivariate Gaussian distribution. And what we show in the one-dimensional case is that you can exactly compute this time, T, but you cannot estimate exactly or analytically in a high-dimensional diffusion model, because that's basically intractable to compute the log probability at any time t. So you cannot compute exactly the marginal for that. So what we did empirically is to run an ablation for different times. And then what we found is that at some point, this, as I showed you in the FID curves, as maybe you remember, there is this sharp decrease in performance. And so, yeah, but I have here a demo. You can find a demo that I have here. But so essentially, that you found is that these samplers, for example, here, what we found to be successful is that around time 500, for example, in the case of Celebrity A, is where the critical point takes place. So essentially, you can get rid of, so you can just speed up sampling by half, right? Just by using the Gaussian later start initialization. So which I think that's a pretty good insight, because people have trying to improve. I don't know if you can see that in my screen or not.
Yeah.
Can you see the collab?
Yeah.
Yeah. So you see here that the initial time start is 500. So that means that just by these insights, you don't need to inefficiently use 500 denoising steps. So you can just run the sampler starting at 500. So which I think that's pretty good. And contrary to what people were doing to speed up sampling. And here I also have an example of, for example, that you see that the fast samplers of DDIM, they implicitly start at 800, right? But they just use the isotropic Gaussian distribution as the initial distribution rather than approximate the distribution at this point. So you can just approximate at this point and you will get better performance, because indeed there is this distributional mismatch. But yeah, so regarding to your question, so yeah, so this is an idea. In practice, we found that most of the, maybe I will go to the presentation. Most of the transition happens around 500 or even 400, and you can see that in the FID curves. So that's how you find here. So for example, you see that you need to sample just before this vertical line. So yeah, so in practice, you need to do this kind of an ablation study to see or to analyze the behavior of the bifurcation points. And you see that immediately after 400, the performance goes really poor. So in theory, you should approximate the distribution right before the period of instability. But you can also get that for any other type of data sets by using this Gaussianity test. You also find this, for example, that the Gaussianity remains close to the multivariate Gaussian distribution just before 400. So that's why in those particular cases, we needed to sample at 500. No? And that's also what we found in practice, that the best performance it's at just before 400.
All right. Thanks.
Does that answer your question?
Mm-hmm. Yes. See, there is a raised hand from Sharon.
Yes, thank you, Gabriel. I have a question. It's how many Gaussians did you use?
Sorry?
How many Gaussians did you use to approximate this? Was it?
Oh, it's not a mixture of Gaussians. It's just a Gaussian. It's just
Oh.
Yeah.
Gaussian.
So.
Oh yeah.
Yeah.
Sorry.
So yeah. So that's also nice. I mean, you can also propose to use a mixture of Gaussians, and probably you will get even better performance.
Yeah.
So that's why we think that also just by using, for example, neural network-based model approximators, you can get better results, because here this is just like something very straightforward. It's not even a mixture. It's not even a very complex neural network that approximates the distribution, but you can just probably fit a VAE for that.
Yeah, I was curious. You have these points where indeed your model makes a decision on toward which example to go in your distribution. But at each denoising step, it keeps making some decisions, right? So also in the first few diffusion steps, there are critical points where some examples are more likely and some become less likely. Is that understanding correctly?
In which image maybe?
In general, right? If you have two examples, your critical point is sort of, it's a distribution where it becomes less likely to go into one direction and more likely to go into the other until you can't really go back anymore.
That's exactly the point of the. So I think that's one of the main contributions of the paper, is that before, so people were thinking about denoising as a thing. So people say that the generation is done by iteratively denoising, by iteratively removing the noise.
Yeah.
But our contribution also is to tell, like, this is not fully right. So before this critical area, everything means revert to the fixed point. So it doesn't really matter so much, because before that point, there is no such a thing like a denoising phase. The denoising phase starts after the critical point, because what you have is that if you see this stable point is basically like a source, or so you understand this like a source. So everything remains there, and after that critical point, which happens more around, in the case of the data sets that I showed you, around 500. After that area, it behaves as a denoising phase. So, but maybe to your question is that indeed you cannot sample anymore if you don't sample from that window of instability that we show. And that window of instability in this case is this one. So let me go maybe to the other.
But even like, for example, in the last few denoising steps, when the image is almost fully generated, it's still making some choices, right? There's still some points of instability, but they're less about in the image, but there's still some small choices it makes.
In which ones? Sorry, in the.
Yeah.
Sorry, I couldn't hear good. Can you repeat the question?
No, sorry, it wasn't a proper question. It was me thinking out loud.
No, but you can just say it once again.
Yeah. So even in the last few denoising steps, it's not only denoising; it's also still making some decisions on on where to go in the image. So you
right.
having these
bifurcations. Yes, that's a good point. Yeah. So yeah, so that's exactly what I also maybe I didn't emphasize that, but indeed, so there is like at least one bifurcation, and that's the main one, which that is basically the one that demarcates the spontaneous symmetry breaking. But there could also be other bifurcations, so that's pretty interesting because you have like a branching process there. So you have like so what it tells you is that before this region, nothing interesting happens, but after that region, all these bifurcations takes place. You know, I mean, and this is what people call like this will tell you about the higher frequencies, right? Because you still the model still need to make choices about the features, you know, like for example, of the face, the color of the hair, the shape of the face, and indeed after that critical point, many other bifurcations. There are many other decisions that it needs to make, and therefore there are other points of bifurcation. Yeah, that's a good point.
Thanks for the talk. Learned a lot.
Thank you.
Very cool.
Thank you for listening, and thanks for your questions.
All right, thank you, Gabriel. Just quickly checking if there are more questions.
I hope it was clear, because it could be not that clear.
I think it was very clear. Very nice presentation. And yeah, I think soon you will also present this as a poster, right? A new RIPS.
Yeah, in 4 weeks.
Nice. Then good luck for that. And yeah, thank you for the talk again.
Yeah, and for you guys also, if you want to, as Gianluigi say, like if you want to collaborate with us about diffusion models, if you have any questions, Sharon, we're happy to help.
Yeah, that'd be awesome. Thank you.
We also struggle with these things, right, Gianluigi?
Yeah, of course. Always.
Yeah. Okay, so thanks a lot. Have a nice day.
Thank you.
Bye-bye.